Welcome to this interlude lecture. In this lecture, we'll learn about set theoretic quotienting, or what I call set theoretic quotienting. This lecture will pertain to just about everything, and whenever we talk about quotient spaces in any capacity, this lecture will come into play. But here we will only be talking about sets and functions. When we talk about quotienting in mathematics, it is usually with some richer structure like a linear space or a group or a topological space or some such thing. But here we'll be dealing only with sets, and hence the things here are very, very simple. It may also seem somewhat tautological, but it is a good idea to familiarize oneself with this. So the prerequisites are basically the language of sets, functions, and relations, and especially the notion of equivalence relations. All right, so there are primers available. There are primers available on each of these in the playlist named Kickstart. All right, and I want to also recall, or I don't know if I should say recall, but I want to introduce this notation that if suppose tilde is an equivalence relation on a set X, then the set of all the equivalence classes under this equivalence relation will be denoted by this symbol, which is read X mod tilde. That's how we pronounce. This is supposed to be just a forward slash. Yeah. Okay, so let's keep these things in mind and proceed. So we will be defining fibers of a function. Surely I have done this in my lectures on either on relations or functions. I don't really remember. I mean the primers on relations or functions. I don't really recall, but it's good to revise. So let's do this very, very quickly. So suppose we are given a function from a set X to set Y. Then for a point little y and y, we define the fiber above y. So the fiber above y as this is the notation, and that is the formal definition. So the fiber above y is all the points in X which map to y. To draw an abstract diagram, suppose this is our set X, this is the set Y, and we have a function which takes X to Y, and let's say the point Y is here. So the fiber above Y is nothing but all those points in the domain which map to Y. All right, so it's a collection of points it's the collection of points which map to Y. This may very well be the empty set because the point Y may not be in the image of F at all. So this may be the empty set. This could also be the entire set X, in which case the function F takes only one value, namely the value Y. Okay, so very simple definition. This is also called the preimage of little y. The notion of preimage is a little bit more general. If you have any subset of the target set Y, you can talk about the preimage, which, as you may recall, is all those points which map inside S. Right? Fine. So that's just a small recollection of the notion of fiber. Let's also see some examples. So this is a map from R2 to R, which is defined via this recipe. So what are the fibers? So what are all the points that map to 0? Those are the points where X equals Y. So this line. So this entire line, or let me make a better line. Yeah, this one. So this entirely maps to 0, and that therefore I'll label a 0 here. And to draw one more fiber, all of these points, they map to -1, where this is supposed to be the point 0, 1. So all of these points map to -1, and similarly all of these points map to 1. So here in this case, the fibers can be identified very easily. They are very nice, just parallel lines. Those are the fibers of the function f. Right? All right. So the fiber above 0 is this, fiber above 1 is that, fiber above -1 is that, and so on. I mean, 1, -1, and 0 are just 3 examples. For any real number, you can take the fiber above that and you'll get a line. All right. Another example is this map, which is even simpler than the first one. It just drops the second coordinate. All right. So here one can actually see the fibers in an even easier way. For any point, I mean, just look at this figure. For any point on the real line, the fiber above that is just the line above it in this diagram. So think about it. And here, in fact, they look a lot like fibers. So this looks like a fiber indeed, right? So that's how this terminology kind of comes from. But anyway, so now let's move on. The fibers can be also seen to arise from an equivalence relation called the fiber relation. Again, I think I discussed this in my primers on relations and functions or something, but good to recall. So suppose we are given a function from a set x to a set y, then we define a relation tilde sub f on the domain as follows. So we say x tilde sub f x prime if and only if they have the same image under f. So that's the definition of the fiber relation. You can easily check that this is an equivalence relation. And the other thing you can check is that the fibers, or rather I should say the non-empty fibers, are precisely the equivalence classes under the fiber relation. Right, so this is the fiber relation, and it is an equivalence relation, and the non-empty fibers are precisely the equivalence classes under this relation. So there is an equivalence relation which gives rise to all the non-empty fibers. Okay, so now for the main point of this lecture, which is set theoretic quotienting. So suppose we are given a function f from a set x to a set y, then what one can do is one can partition the set x into fibers. One way to see is why the fibers partition the set x is just, just take the definition of fibers and you can see it. Or you can note that non-empty fibers are precisely the equivalence classes under a certain equivalence relation called the fiber relation. And hence non-empty fibers partition the entire domain, because equivalence classes always partition the set on which you define the relation. So the set X gets partitioned into equivalence classes. There are too many of them, but what can you do? So this is one equivalence class. This is obviously just a suggestive figure. We don't need to take it very seriously geometrically. This is another equivalence class and so on, ... So just collect the equivalence classes as points of a different set. So now since I have too many of them, I'm going to regret. Yeah, so this is a set which is nothing but the collection of all the fibers, non-empty fibers of F. So this is nothing but X mod the fiber relation. So that's a set that we can create. And now there is a natural map from X to this set, which is denoted by pi. And what does it do? It takes little x and outputs the equivalence class in which x lies. Equivalence class under the fiber relation, of course. So in other words, it takes x and outputs the fiber in which x lies. So suppose x is here, then the output is this thing, this entire thing. Okay? So very simple map. And the point of all this is that there is a unique map here. There is a unique map here. Sorry. Which we will denote by f bar. So there is a unique map f bar from the set of all the non-empty fibers to I such that this diagram commutes. What does that mean? It means that whether you start with a point here and apply f, or you go via this two-road route, you will always land on the same thing. So what is this map? We can just define what this map is. So define, or before I continue, let me just draw the more abstract diagram. It was already abstract, but this is a little bit even more abstract. Yeah. So how do we show that such a f bar exists? We will just construct it, and the uniqueness is very, very simple. So define f bar as follows. F of the equivalence class under x, f bar of the equivalence class under x is same as fx. Right? So that's our definition. In fact, this is the only possible definition. If at all there is such an f bar, it has to satisfy this, because if you start with x, you end at f of x under this road. But if you take this road, you first become the equivalence class of x, and then you become the image of the equivalence class of x under f bar, and therefore the image of the equivalence class of x under f bar must be equal to f of x. So there is only one candidate for f bar. The problem or the issue here is that this is defined via representatives. You pick an element of the domain here, and then you choose a representative of it, representative of this thing, which is an equivalence class under a certain relation, and using that representative, you define what the output is. So it is not immediately clear why f bar is well defined, but that's actually very, very easy, because suppose, so I'm arguing well definedness. So if this were the case, suppose you have two things which with the same equivalence class, then what do we want to show? We want to show that f of x is equal to f of x prime. That is exactly what it means to say that this guy is well defined. But what does it mean to say that x and x prime have the same equivalence class? It means x and x prime are in the same fibers, and that exactly means that they have the same image. So then f of x equals f of x prime, and hence f bar of that element is f bar of this element, and hence f bar is well defined. So very simple, right? And this is set theoretic quotienting. Again, as I said, this is a trivial fact, but you will see when we export this to more complicated settings. So once again, you have some arbitrary function f. What you do is you can factor it out via the set of all the fibers. This is the language we use. The map f is the map f factors through the set of all the equivalence classes under the fiber relation, or in other words, by factors through the set of all the non-empty fibers. It's getting factored into two parts. One is this map, which one also calls natural projection map, and this is the map that is induced by f from this to that. Okay, and let us note one thing. Note that this guy is injected. So the philosophical way to look at it is the following. F introduced some identifications in the domain. The map F is or can be thought of as a device to assign names to things in the domain, but it is not very faithful to the members of the set, meaning it may assign the same names to different objects. But what does this guy do? It just keeps track of what, or rather it records exactly what F had forgotten. And once that forgetfulness has happened, the map F bar now is kind of trying to redeem or not falling for the same dementia kind of thing that F has fallen for. So this just tells you that no more forgetting. We have forgotten what we had forgotten, but no more forgetting. So that's a very philosophical high-level answer to it. The mathematical answer would be to write a proof of it. And the proof is very, very simple. So if F bar of this guy is equal to F bar of that guy, we want to show that this is equal to that what it means to say F bar is injective. But this implies, by definition, this is the case. Oh, sorry, I don't want to write a y. I want to write x prime. So which by definition means this is the case, which means x and x prime are in the same fiber, which is to say this. So that shows injectivity of the function f. So that's very simple. So any function f factors through this set via an injective function. Okay, so this gets embedded inside that, if that makes sense. All right, so this is your basic set theoretic quotienting. We can say a little bit more. So before we do that, we need to talk about a certain notion in the context of relations. So suppose we have two equivalence relations, tilde and I don't know how to read this. This is, I'll say, congruent. So tilde and congruent are two equivalence relations on the same set X. Then we say that congruent is finer than tilde if each equivalence class under congruent is finer, or sorry, is contained in some equivalence class under tilde. So this is not saying anything very complicated. You have some set X and there is some equivalence relation tilde, so it partitions the set X into some parts. And now you have some relation, equivalence relation congruent. What it does, it partitions it into finer parts, meaning each equivalence class under tilde is now getting partitioned by the congruent thing. So that's why congruent is called finer. It is giving you more finer information about the set X. Of course, the finest equivalence relation would be the one which doesn't do anything, meaning x tilde x prime. Okay, let me not use tilde. So let's say R is a relation such that defined in this way, such where x is related to x prime if and only if x equals x prime. So this is of course the finest relation that you can have on a set X. Nothing is finer than that. But I hope this definition is clear. All right, so that's the notion of fineness. You can develop synonyms for it. So we say this is finer than that, if that is coarser than that, and so on. So those things follow automatically. And now we can talk about the more general set theoretic quotienting. So the general thing is the following, or let me write here. So this will be more or less an exercise for you. So let's say again we have some function from x to y. And suppose we have a relation congruent is an equivalence relation on x such that this is finer than the fiber relation on X. Fiber relation induced by F, of course. So then the map F factors through this guy, X mod congruent, and we use the same symbol pi. Pi this time takes X to the equivalence class of X under congruent, not under the fiber relation, but under congruent. And we do get a map in this way, F bar, which this time is not an injective map. This does the same thing. It takes the equivalence class of X and sends it to Fx, and this is well defined. You can prove that, and this diagram commutes. But this is no longer injective, because the identifications made by congruent are not as forgetful as the identifications made by the map F, and hence there is more room for F bar to forget, so that the forgetfulness here adds up to the total forgetfulness. Therefore, this is not quite injective. Not necessarily, I mean. So that's our map F bar, and this is a more general version of the offset theoretic quotienting. So just ponder upon it, and with that I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.